Everyone, on behalf of the Universidad de las Americas and Ensure 6G Consortium, it is a great pleasure to welcome to the second day of our training module titled Advanced Wireless Network Security and Privacy, part of the Horizon Europe Marie Curie Staff Exchange Project Ensure 6G. The Ensure 6G project is a multidisciplinary expertise from 15 institutions across Europe, Asia, and Latin America. Through collaboration between academic and industrial partners, the project focuses on developing innovative, trustworthy, and human-centric security and privacy solutions for future 6G networks. Focusing on a driving solution, robust network infrastructure, quantum encryption, ethical frameworks, sustainable business model, and sector-specific insight. The consortium adopts a holistic approach to creating secure, resilient, and innovative 6G ecosystem. Good morning again, and welcome to the second day for our training module Advanced Wireless Network Security and Privacy. We are excited to continue this important conversation after giving some introduction about the project. On Tuesday, we had the pleasure of hearing from Professor Anne Bracken, who introduced us to the fundamental mechanism of security in 5G and 6G network. Her talk provides a solid foundation by highlighting the evolving threat landscape, the role of cryptography methods, and the importance of integrated resilient security framework as we move toward hyper-connected. Also talk about the AI-enabled systems. Yeah. Today, we will take this discussion further for exploring more advanced and interdisciplinary perspectives. We will address key challenges in AI-driven threat detection, ethical concern, federate learning for privacy preservation, regulatory frameworks, and IoT-specific security in 6G environments. These are critical topics to not only for technical design, but also for shaping trustworthy and sustainable digital infrastructure for the future. Let's start. We will start with the Professor Shen Wang in the University College Dublin. We will have the speaker with the Federate Learning for Privacy Preserving 6G IE system. For the professor, Dr. Shen Wang is assistant professor and academic director of NetSlab Research Group, a School of Computer Science, University College Dublin, Ireland. He is a senior member of IEEE and an active member of its Intelligence Transport System ITS Society. He received a master's degree from Wuhan University, China, and PhD degree from Dublin City University, Ireland. Dr. Wang has been involved with several Europe projects as a COPI, WP, and task leader in big data streaming for air traffic control and trustworthy AI for intelligent cybersecurity systems. Some key industry partners of his applied research project are IBM Research Brazil, Bain Research and Technology Europe, Telefonica Research, and Fraunhofer Focus. His research interests include connected autonomous vehicles, explainable artificial intelligence, and security and privacy for mobile networks. Welcome, Dr. Shen, and you can start with your presentation. Thank you very much to be here with us today.
Thank you, Paula, for introducing me to everyone. Good morning or good afternoon, everyone, depends on where you are. So I'm trying to share my screen, and please let me know if my sharing is working. So yeah, I hope you can see my slides in the right mode, or in a presenter mode, or is in a...
It's correct, Shen. It's
okay. Yeah, it's okay.
It's a correct one, right? Great, thank you. Okay, so yeah, my talk today will be about federated learning for privacy-preserving 6G AI systems. So, um, firstly, let's take a look at the basic concept of federated learning. So, federated learning is a type of distributed machine learning. So, what the distributed machine learning is doing is they basically have these kind of data owners placed all across different locations, and but they all very well connected to the training infrastructure. So even the data, distributed data owners, they own the data and host the data in the superpower machine. And these superpower machines are connected with the high-speed fiber or other connection materials that is not via the public internet. So because previously, although it's called centralized learning, but all this kind of data and also these distributed machines are owned by one giant entity. For example, Microsoft or Amazon, they have their own machines everywhere, but they are the single owner of the data. They are the single owner of the training infrastructure. So they can do this thing in this way, right? They start asking the data from wherever this data is generated and collected and then sent to the training infrastructure and then train their model. Okay, so that's the traditional distributed, or you can also call it centralized learning because everything is owned by the single entity. And why it motivates the emergence of so-called federated learning is because once we're trying to push this data owner to the edge, to the end user, where this device and also where the data is originally collected is not owned by the single entity. Then, if we still continue to keep this paradigm working, then we are facing a very serious data privacy issue because wherever this data is originated from, then it has to communicate not through your proprietary communication infrastructure. It will be through the public internet, and you will facing the high risk of getting your personal data lost or hacked by the third party. So, is there any computations system or schema that can avoid this thing happen? Then this motivates the invention of federated learning, so that where the data is originated or generated, the data can always stay untouched or unmoved. Then using this new distributed machine learning training scheme. We call it federated learning. The data stays where it collected, and between the data owner and the aggregation server, the things transmitted are only model updates. Because as we all know that machine learning done the same thing iteratively, one round after another. Basically, sometimes may need hundreds of rounds, sometimes may need thousands or even millions of rounds, depends on how difficult your task is. So um, because the data itself will never appear on the or exposed to the public internet, thus this is very promising for the future um, uh, digital era where the personal data's privacy is of uttermost, especially when the data owner is a mobile end user where you take a lot of your personal live photo, or the organizations such as the bank and hospital where these personal data when it's collected and it has to stay away from the digital world. Okay, so how it is getting trained. So this algorithm called FATF, Federated Average, is full name. So this is one of the most commonly used federated learning training paradigm. So basically, let's say on the first step of FedF is from the server. So firstly, the first step is central server choose a statistical model to be trained. So normally when we're referring to the machine learning model, it is the classifier. So this refers to the classifier decision boundary. Okay, the second step is this server sends this model, the same model to all the worker machine or the client. As you can see that everyone has the same copy of the same model. Well, what's different is this step 3, each one of the client has different portions of their data. So they all have collected their own data. That is why, normally their data distribution is a bit different. So, and then step 3, the main task of step 3 is they all do the training locally in parallel. Therefore, compared to step 3, you will not see any communications happen, right? There is no communication happen between server and clients, even among clients. And because their data are different, therefore, after training, the classifier on each client side is different. So each client have their own different models. While to proceed to step 4, then each one of the clients still have their own different models, but they need to use the communication infrastructure again to send everything up to the aggregation server, and then the aggregation server have each one of their copy and then make the average, and then that's the agreed or aggregated global model for the next iteration step. So that is called federated average. What is transmitted in between server and clients is always model updates, right? So everything seems great because the data will never move until we find mathematically that it is probably not the case. Here we take a relatively easier problem, right? So let's see, we are training a regression model, and the loss function is the least square. Okay, so we're trying to minimize this loss function, where this loss function equals to this least square function. So we're trying to minimize that. And then remember, normally, according to the mathematical notation, this xi is the data and yi is the label of the data. So when we take the derivative of this loss function, we find that this is a gradient and this is the updated model one round after another, right? So this data is just a kind of transformation of these. Okay, so the transformation of the data itself, will be leading directly to the model update, to the gradient, and the gradient will be a kind of linear transformation back to the model update. So which means that although this transformation is non-linear from the data directly to the gradient, but the transformation is actually very clearly defined here. So it is actually theoretically possible that once you get not the data, but the model updates iteration by iteration, you will normally know how to reconstruct the real data that you thought is never being transmitted over the public internet, but accordingly you will find a way to reconstruct it. So which means privacy risk are still there, although it's not that straightforward, but it's still there. How to protect it. And there are a few more challenges when we are deploying federated learning in 6G era. So Traditionally, in 6G or non-6G era, faculty learning challenges, there's always about communication overhead. So the communication overhead, why is that the issue? Is because, look, again, these gradients or the local updates share the same dimension of the data. So although you are not transforming the data, but they're sharing the same dimension of the data. So which means that the model updates that you're transmitting is not small. And what's more important in 6G era, 6G guarantees the high bandwidth, low latency again. So which means hopefully this communication overhead issue will be mitigated. However, these massive connections and this, trying to connect everywhere promise will bring up this heterogeneity issue to the more challenging level. So the data heterogeneity means, these different type of label data will be different across different machines, and also the quantity, So the type of the data and the quantity of the data distribution, the heterogeneity level is very high. How to deal with that? And also the device. Some device could be the smartphone, outdated smartphone. Some device could still be the a mini-scale superpower machine. So, which means that after the single local training round, some device can finish the a single training very quickly than the other slow device, but they all have to wait for the slowest device to finish the single round, the current round of iteration, and then submit to the central server together. If not, then we can go to a synchronous Federate learning. But because 6G trying to connect all types of devices, this gap will be huge. So how to make the trade-off is another challenge. Okay, so I think I have covered all the basics of the, what is Federate learning, why Federate learning is more challenging in 6G. Hello? Yeah. Now let's have a quick look at I think someone of us, yeah, okay, great.
Sorry.
Yeah, no problem. No problem. So I will quickly go through series of Federate learning works that has been done in our Nest lab in recent years. Okay, so firstly, the work that I want to introduce is called RecDef. So as you can see that Federate learning, these model updates transmission happened over time, right? But before this work, we haven't seen any data reconstruction attack is actually focusing on these time series things. So over the whole training round. So we firstly study this type of attack in the use case of VR based IoT consumer scenario, and then we demonstrate how risky it is to use this data reconstruction attack on that. And also we propose a new recommendation framework for privacy update. So sometimes when you trying to add more noise to the updates, then you find your model is not working. So too much noise can preserve your private data, but it can deteriorate your model performance. So as you can see here, those are highlighted results. If we add no noise, you can see after several iterations, these ground truth data will be successfully reconstructed. But while we are trying to increase these noise, even up to 10%, this data reconstruction attack will not work. And also compared to other framework, our methodology will not impact this model performance across the time. So, which again demonstrate the effectiveness of our method from other angle. Right. So that's the first work. The second work I would like to share with you is called Shield. So this is published by in a top journal in security and privacy domain. This work basically focusing on a new Federate learning paradigm called hierarchical Federate learning, which means the system architecture we're focusing on is not just about two layers from server to the end user. It is focusing on more, including more middle layers, so which which will be more popularly seen in 6G area because in 6G area we will see a lot of connections, and if the central server needs to handle all these connections, they will create a lot burden to the central aggregation server to handle. Therefore, we introduce one layer or more than one layer in between. So this work is not only focusing on three-layer hierarchical Federate learning, focus on whatever layers that you would like to introduce in between. So it is quite general. And also, this work is demonstrated on different types of heterogeneous network. Depends on where these poisoner users are from, and also depends on where this data is distributed. So we introduce this alpha from data clay distribution. So the smaller the alpha is, the more diverse the data distribution is. And so basically the shard works in a way like, okay, so we still follow the traditional way where the central server send the global model first, and then each client, including the poisoned, compromised clients, training their model locally, and then once they send their update for the first to the first layer, then the first layer machine start to use HTTP scan to find and remove the outliers. And up until the central server holds the global model for the previous round. And up to the central server will be checking this distance-based calculation rather than running the HTTP scan for all the middle layers for model aggregation. So we have tested this methodology very comprehensively and against the state-of-the-art solution. And we have this recommended use of our shelled method in a full spectrum. Depends on the percentage of the poisoned users, and also depends on how your data set is distributed. Okay, so that's the second work, shelled focus on hierarchical Federate learning. The third work that I would like to share with you today is called Shepra. So the key highlight of this work is to use explainable AI and trying to get these justifications for the machine learning model to make their decision. And then using these justifications, by using these justifications, we can try to fill up the existing gaps for the work, for the SOTA work. So we can see that there are two types of the SOTA work. The first type is his history-based repetition scores, for example, full scores. The downside of that is if the new client is added. Imagine that in a large scale of distributed Federate learning training network, you cannot guarantee that always these users are not changed. So in practice, the users leaves, joins and leaves from time to time. So if a new client is added, then we have no prior history of it. So then it makes full scale hard to run, and also including full scale Chrome and Flame, they are using similarity based metrics, which means that if the majority of the clients is malicious, then this method is hard to work. So what we are doing is we for the specific machine learning task, we have a highly trustworthy small sample, and then we identify the behavior of the machine learning model, and we extract the so-called correct justification, and then we deployed it on the aggregator side, and then the aggregator side would have the not just about these client updates, but also the justification on how AI decision is making, how the correct AI decision is making. So then it is actually quite good that to show that it is effective across all the poisoned clients. So compared to the previous one, Shelled, the percentage of poisoned users, when it goes large, it is still not very good to handle it. However, Shapra is quite good in full spectrum of the percentage of compromised clients. So the last but not least is the work that I would like to share with you. Is the peer-to-peer fallacy learning. So it's a full distributed fallacy learning network. So this is the initial work. We are open for more collaborations so far. So we so this one is like we don't rely on the central server anymore, since fallacy learning is a type of distributed machine learning. So why not make it more distributed? Let's try the fully distributed one, so that each one of the node will have to engage in the training process, and also will have to engage with this model aggregation process. So then how to ensure its efficiency, and also how to ensure the privacy and security on the quite dynamic and sensitive network topology is kind of challenging things we need to face. So yeah, basically, this is more like a peer-to-peer fallacy learning implementation, and we are playing around the parameters about network topology. And interestingly, we find that that peer-to-peer fallacy learning actually converges very quickly compared to the centralized or traditional fallacy learning paradigm. So we also find that if you are allowing exchange of the model update from two of your neighbors rather than five, two actually converges even faster. The smaller number of neighbors you're communicating with, the faster it get converged. Which also, is an interesting finding, because we can see that if when we are considering the fully distributed network, you cannot assume everyone is fully connected. Otherwise, the whole network complexity will be very, very high. And we see that with and without differential privacy, which is basically adding more noise to make the model updates more secure, has no impact on this model accuracy. The final converged model accuracy still remains. Of course, this work needs to be tested more under more extreme scenarios, but this is the initial work that I would like to share with all of you. Okay, so that's everything I want to say today. Hope you enjoyed it, and I'm happy for any questions that you have for my talk, and also this series of fallacy learning related work from UCD NetLab. Thank you.
Thank you very much, Dr. Shen. here there is some there are some questions, please. How does the federated learning enhance privacy compared to the traditional machine learning approaches?
Yeah, so the traditional machine learning approach, this all backs to the very beginning, right? So the the data stays, the traditional machine learning data always stay physically in the machine, while federated learning, the traditional machine learning, the data stays here, and also while we are training the model, the data um, moving over the wire, over the connection, over the public internet, whatever, over this communication wire or wireless channels. So, which means that, it is exposed for the attacker to launch any kind of attack. So any kind of attack that is successfully launched, they will get the data directly from this training period. While federated learning has this data physically stayed while you are training machine learning model, it is still unmoved here. Although I said, later, we are still facing the privacy leakage risks, but model updates, you still need to accumulate that model updates over the time. You still need to launch a sophisticated, customized or specifically designed data reconstruction model to do that. So it is still like, attacker needs to cost something. So that is why federated learning is still a good one to preserve the data owner's privacy compared to the traditional machine learning paradigm. Okay.
Yeah, sure. Thank you very much. Here is another question. What are the biggest technical barriers in implementing federated learning in real-world 6G systems?
Yeah, so I think according to my knowledge, this is all about the scale and also all about this data owner. So the federated learning is not largely deployed is because when we largely deployed federated learning, there are a lot of different types of data owners, and each data owners needs to know that okay, their privacy is preserved physically, but they also need to be aware that what are potential risks of having using your data, and uh, so your data will be used, but your data will be staying. So, it's hard to explain it to the end user that, okay, this data, will be always stay in your machine, but will be kind of used by us. So, and the more data owner, the larger the scale is, the more challenge that you will be facing by this heterogeneity challenges, right? So you will definitely need to go for asynchronous federated learning in order to make your training process uninterrupted or smoothly finished. But if you are federated learning up to the very large scale, then it's very hard to predict this gap. So when the gap gets bigger, then there are a lot of unexpected things happen, and then you need to spend a lot of time of your engineers to tune it. So far, the successful deployment of federated learning is not for the big scale, but so far in a kind of sandbox or enclosed scenario, it is working very good. I've heard some successful cases in bank and also hospital. So these data owners are all hospital, but different hospitals, which means these federated learning clients are not so so much. But because smart health, we need different hospitals to exchange the data, but they don't want. But okay, you don't need to exchange the data, but you can, share the access of your data while we're training the model. The model can be shared. The model is not trained by your data only; it's trained by everybody's data. So then, this one works great, and also this one was great. But all these two successful cases does not have a lot of data owners. That only about 10 or 20 something. Okay, yeah. Hopefully it answers your question.
Yeah, surely it was very clear. Thank you so much. I don't know if someone want to add something else. Yeah. Thank you very much, Dr. Shen. It was
Thank you, Paula.
very
Thank you,
pleasure
everyone.
that you give us and share with us your work and so good.